Today we're going to look at Fermat's method for calculating the integral of x to the n. And what's really nice about this method is it splits our region of integration into rectangles, much like Riemann's method. But what it does is it makes those rectangles smaller multiplicatively instead of additively. So what do I really mean by that? Well, let's maybe partition this interval from 0 to a into points by multiplying by q, where q is less than 1. So notice over here on the right, we've got the point a, so that's our right-hand endpoint. But then since q is less than 1, we have q times a to the left. And then q squared times a is to the left of that. And then q cubed times a is to the left of that. And notice as n goes to infinity, q to the n will go to 0, so that'll like go way back to the origin over there. And then we make our rectangles out of these points. So our first rectangle will be between q times a, and we'll take a height of, well, that'll be a height of a to the n, given that our function is x to the n. And then our second rectangle will be between q squared a and q times a, and it'll have a height of q times a all raised to the n power, again because of our function. And then we continue back to the left, making an infinite sum. And this infinite sum will approximate the value of our integral. Okay, and then as you can see, as q approaches 1, the approximation becomes closer and closer and closer to the actual area under the curve. In other words, the actual value of the integral, thus, giving us that area under the curve via this nice, maybe non-standard method. Okay, so let's see this in action. So we've got this integral from 0 to a of x to the n will be approximately equal to the sum of the area of these rectangles, where we're taking q to be smaller than 1, but maybe close to 1. So let's see, like we said before, the area of this first rectangle will be a to the n, that's the height. And then it'll be times, let's see, a minus q times a, that's the width. So like I said, that's our first rectangle. And then our second rectangle will have height, let's see, it's a to the n times q to the n, because notice that brings us way up here. And then it'll have width of q times a minus q squared times a. And then let's put one more in there. So our next rectangle will have width, well, it's q squared a all raised to the n, so that'll be a to the n q to the 2n. And then next we'll have, let's see, q squared a minus q cubed a. And then that's going to continue on and on and on. And notice that even if q is maybe a half, so that's fairly far away from 1, we still get an infinite sum. So instead of like with Riemann sums, we approximate it with finitely many rectangles, we're always approximating it with infinitely many rectangles here. Okay, so let's maybe factor out as much as we can from this infinite sum. So note that we can factor an a to the n out of everything. We can also factor an a out of everything because both of these terms have an a, both of these terms have an a, and so on and so forth. So in the end, we can factor an a to the n plus 1 out of everything. So let's see what we're left with after that. So for this first bit, we'll have 1 minus q. And then let's see, for this second bit, we'll have q to the n plus 1 times 1 minus q. So we get a q to the n here, and then a q from the inside. And then for the next term, we'll have a q to the 2n plus 2 times a 1 minus q, and so on and so forth. So let's see, we have a q to the 2n from there, and then a q squared on the inside. But now we can factor a 1 minus q out. So that'll leave us with a to the n plus 1 times 1 minus q times, now we'll have 1 plus q to the n plus 1 plus, I'm going to write this as q to the n plus 1 all squared, and then you can probably guess my next term will be q to the n plus 1 all cubed, so on and so forth. But what do we have here? Well, we've got a geometric series. So let's point that out. Here's a geometric series. And what's our common ratio? I'll call our common ratio R, but it's pretty clearly q to the n plus 1. But luckily, since we verbally chose q to be smaller than 1, but close to 1, that means that this common ratio is in the region of convergence. So that means we can apply the formula for sum of a geometric series to get us there. So let's do that. So here we'll have all of this is equal to a to the n plus 1. We have 1 minus q, and then the sum of this geometric series will be 1 over 1 minus q to the n plus 1. Okay, but now let's rewrite this as a to the n plus 1, and then we'll have 1 minus q over, but we can factor 1 minus q out of this 1 minus q to the n plus 1 fairly easily. And that'll be 1 minus q times 1 plus q squared. And where is that going to end? That's going to end at q to the n. Oh, but notice we get some nice cancellation here. This 1 minus q here cancels this 1 minus q here, leaving us a 1 in the numerator. So in the end, we have a to the n plus 1 over this sum, starting at 1 and ending at q to the n. But like I said, we'll get the actual value of this integral, in other words, the actual area under the curve, in the limit as q approaches 1. So let's see what we get when q approaches 1. Well, I think it's pretty clear we're going to have a to the n plus 1 over n plus 1, because we've got a sum of n plus 1 things in the denominator, all that are approaching 1. But let's look at this. So we've got this integral from 0 to a of x to the n dx on the left-hand side, and we've got this a to the n plus 1 over n plus 1 on the right-hand side. But that's what we would expect from the power rule for antiderivatives and the fundamental theorem of calculus. So there we did it. We calculated this integral using Fermat's method, and well, we got the same answer that we would expect, which is a good thing. Okay, so now let's repeat this for maybe a negative value of n and see what happens there. Now let's look at the case when we have a negative exponent. In other words, we look at the integral from a to infinity of 1 over x to the n. So notice our bounds of integration are a little bit different here, but this corresponds to the new choice of n. And we'll see along the way that we'll actually need n to be bigger than 1 here, which of course you can check via like standard calculus methods, but I think it's nice to see this via Fermat's method in this case. Okay, so here we're going to do something very, very similar. So we're going to split this into rectangles just like we did before, but now instead of q being close to 1 but smaller than 1, we'll want q to be close to 1 but larger than 1. So that means if we start at a here, q times a will be larger. Q squared times a will be even larger, and then so on and so forth. But as q approaches 1, well, that's going to squeeze all of those rectangles together and turn our approximation into, well, the exact value of the integral. Okay, so let's see if we can get the same result that we expect using this method now. So we've got the integral from a to infinity of x to the n dx. So this will be approximately equal to, so let's take the area of the first rectangle. Notice the height here is 1 over a to the n, because our function here is 1 over x to the n, and then the width is q to the a minus a. So q times a minus a. Good. And then the second rectangle, well, that has height q times a all to the n power. In other words, 1 over q to the n, a to the n. And then the width will be q squared a minus q times a. So let's write that. Q squared a minus q times a. And then we'll write one more. So let's see, for our one more, we'll have a height of 1 over q to the 2n, a to the n. And then we'll have q cubed a minus q squared a. And then so on and so forth. That's going to continue forever. Again, instead of approximating this with finitely many rectangles and taking a limit, we're still approximating this with infinitely many rectangles. Okay, so now let's factor some stuff out. Notice that we can first factor a 1 over a to the n minus 1 out. So we've got an a to the n in the denominator and then an a in the numerator for all of these. So what does that leave us with? So let's see, for this first bit, we'll have a q minus 1. And then for this second bit, we'll have a 1 over q to the n minus 1 times q minus 1. So the q to the n comes from here, and then a q in the numerator comes from factoring it out of that, q squared a minus q times a. And then let's see what we have next. So next we'll have 1 over q to the 2n minus 2 times q minus 1 for a similar reason. And then that continues on and on and on. But now here we can factor out a q minus 1. So that'll leave us with a q minus 1 in the numerator over a to the n minus 1, and then a 1, and then we'll have plus, let's see, 1 over q to the n minus 1, and then I'll write this as 1 over q to the n minus 1 all squared, and then the next one will be 1 over q to the n minus 1 all cubed, and so on and so forth. But let's see what we have here. We've got another geometric series. Now the common ratio is 1 over q to the n minus 1. But since we've taken q to be close to 1 but larger than 1, then we know that 1 over q is, well, it's between 0 and 1. So we're in that region of convergence. So we can apply the rule for geometric series, and we'll have this thing out front, q to the n minus 1 or over a n minus 1, or q minus 1 over a to the n minus 1. And then we'll have 1 over 1 minus the common ratio, so that'll be something like this. But now let's simplify that next term. That's going to leave us with 1 over q, or a to the n minus 1, and then we'll have a q minus 1 over here, a q to the n minus 1 over here, and then a q to the n minus 1 here. So that's just doing a little bit of arithmetic. Okay. But now we can simplify this term that I'm boxing in peach pretty similarly to what we did before. And this will simplify to 1 over 1 plus q plus all the way up to q to the n minus 2. And then if we let q approach 1, what do we end up with? Well, this q to the n minus 1 will approach 1. And then we'll be left with 1 over n minus 1, which we're getting from this term over here, and then 1 over a to the n minus 1, which is, again, what we would expect using standard methods for calculating this integral here. And now let's look back and notice that we never used the fact that n was bigger than 1. Oh, but we actually did. Because notice if n is equal to 1 here, then that means this q to the n minus 1 is 1. But then that means this q to the n minus 1 squared is also 1, and then this is also 1. And we've got a sum of just a bunch of 1s, which clearly diverges. So that means we were not able to apply the geometric series rule in that case. So we implicitly used it without really thinking about it that much. So that maybe like patches that little problem here. This actually n has to be bigger than 1. Okay, so if you're still around and you haven't subscribed, maybe consider subscribing. It really helps us out, and that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.